All right, I will go ahead and get started. Welcome to Test 2 review for 3146. In this review session, we will be going over multi-threading, C++ pthread data sharing overview and examples, and CPU scheduling and examples. Pthreads are just a thread of a process. You can have multiple of these threads running on a single process, and this is called multi-threading. The main function itself is also a thread that is just controlling the other threads, well, creating the other threads. And we do that through pthread underscore create. To use pthreads, we need to include the pthread.h in our C++. And whenever we compile this C++, we need to include the -l pthread for C++ to recognize it. Function headers for pthreads are going to be void star functions with void star arguments. And to create a pthread, we just use the pthread create, the ID. The second parameter can be null. The function we will be passing to the pthread and the arguments for that function. And just here's a further breakdown on the pthread create. We have the ID. This is actually an attributes field. The function, and then the args for that function. So more about the void star. Void star is just a pointer that can be of any data type. So it has no data type associated with it. It could be an int, a double, a string, anything under the sun. And here's an example of casting this int x to this pointer and then converting that int pointer into the void star pointer. And then we can then use that void star pointer of x to then plug it into this function. The structs in C++ are just a data type with other data types contained within them. So here we have my args. So we arg1, arg2, and then over on the right side we have the declaration of my args, where we set arg1 to 10 and then arg2 to the character y. And then here we are passing the struct into a void star pointer, which would then allow us to pass it into a pthread function. That's very useful. And I will pass data sharing off to Himeth.
All right. So data sharing, our threads can share data, and that little section in our code that involves with share data, usually a global variable or something, uh, that's called our critical region. And if you have multiple threads in the critical region, it can lead to some conflicts, as you might have seen in some of your previous assignments, such as data strict alternation, Peterson, and OS call, those program assignments you did. And then when you have multiple threads in the critical region and they end up with different values or results, we call that a race condition. Now, when we're dealing with threads, there's certain principles we want to ensure that are being enforced, and that's our mutual exclusion principles. So the first one is no two threads or processes can be in the critical region at the same time. We don't want that happening at all. And then no assumptions must be made about the hardware. You can't assume that your user has like the best hardware or like the worst. You just can't take that in as a factor. Um, then a thread or a process that's not in the critical region, that should not stop another thread or a process from entering. And then no thread or process should have to wait forever to enter a critical section. They should, at some point in time, be able to enter the critical region and do whatever they need to do. So one of the first and most simplest data sharing things we have is strict alternation. So essentially, we're just taking the threads are just taking turns, right? Thread zero does its turn, it does its stuff in the critical region, and then once turn zero or thread zero is done, thread one can do its stuff. And essentially, it's really simple, right? You have that while loop where if the turn is not equal to the thread ID, that thread's going to be stuck in the while loop iterating. The thread that does match the turn, that will do its stuff in the critical region, and then after it executes the critical region, it'll change turn to the other value, and then the thread that was stuck in the while loop can do its stuff. And this is just an example of strict alternation in the code. So as you can see at line 14, right, you have your while loop. That's where the thread that's not that it's not their turn yet. That's where it's waiting. That count plus plus and std c out. That's your critical region right there. Because as you can see at the very top at lines 5 and 6, count is count is a global variable, right? So because of that, you would consider that section of code, lines 18 and 19, your critical region. And then after the critical region, you have your if-else statement checking what the value of turn is and changing it so the next thread can have their turn. Yes, why? Uh,
I just wanted to ask, so why did you say that uh, the beginning of the critical region is at line 18?
it's just to make sure that you guys realize where exactly the critical region is, right? Because especially when you get with, say, your producer consumer, you really need to identify where that critical region is, right? Because that impacted where you would put your pthread con wait and pthread con signal. So if you can recognize where the critical region is, it makes doing some of these things a lot easier. Does that answer your question, Lai?
Oh, no, no. I get what you were saying about why it's good to know where it is. I was asking, like, why is it at, like
Oh, yeah.
18?
So, like I said, at line 5, you see int count being declared, and it's outside of any function, meaning it's global, right? Anything inside this program can access it. And because anything can, since it's global, right? That's your critical region, right? You, if we didn't have, in this case, strict alternation, you could have two threads accessing count at the same time if we didn't have the strict alternation, right? And we could get something like that race condition from the previous slide where the two threads might have different values, or you might have where you've seen in one of those example outputs where sometimes it would just count the same number twice. I'm pretty sure you guys remember that from your program assignments when you had to take a look at the code and see if there's anything wrong with it in the output. So those kinds of things can happen if you don't have like a strict alternation or something going on. And the reason why count is a critical is part of the critical region is because count is a global variable. Does that make it more clear?
Yeah, that makes it more clear. So you're saying it's because we would be able to identify where the global variable is, and
Mm-hmm.
because count is declared outside of the void my function, that's why we said that it's a global variable.
Right. If count was declared inside my function, it wouldn't necessarily matter. It wouldn't really matter if two threads were accessing it at the same time because it would be like it'd be a local variable, right? But since it's global, we need something like strict alternation or mutexes or Petersons to ensure that we have the correct outputs after we run the program.
Okay, and when you say strict alternation, that is just one thread executes at a time. That way, there is not an interleaving that takes place. Am I like summing that up correctly?
Yeah, no, you're right. It's only one thread can be executing at a time, or yeah, executing at a time, because one's either stuck in that while loop and the other one's doing the stuff in the critical region.
Okay, thank you for the clarification.
Yeah, no problem. Okay, and so now we have Peterson's. Peterson's is just an updated, or it's a little bit better version of strict alternation. And this one you have you still have the variable called turn, but this time you also have an array called interested. With Peterson's, you're able to decide if or let the threads decide if they're interested in uh, doing the stuff in the critical region, right? So inside, you can see your void enter region program, right? You have your other, which is just the other processes ID, right? And then we're going around inside the array of interested. We're changing the value for the thread that's interested in running to true so that it can actually do its stuff, right? And then again, you still have that while loop that checks if it's the correct turn and if the thread is interested in running. So the pros of Peterson's is that there's no strict alternation because we have that array that just that shows if the threads are interested in running. But you still have busy waiting here, and that's also the same thing with uh, strict alternation. Again, you have busy waiting where you're still where one thread, if it's not interested, it still has to take its turn before the other thread can do its stuff. And if we go to the next slide, we have mutexes. Okay, and so mutexes are essentially the best solution that we have to this. It's essentially a software lock that acts just like the enter region and leave region from our Petersons. But the crucial difference here is that there's no continuous checking of the mutex, so no busy waiting in this one. It's the best solution that we have. All you need is you need to declare a mutex variable, and you can either do that with the macro at the global level, or you can use the init function in the main. And then you just need your pthread mutex lock and pthread mutex unlock around the critical region. And here's what the locks and unlocks look like. You just have pthread mutex lock, and then inside of it, you have a pthread mutex t pointer uh, call, called whatever you created that mutex variable, right? So if you had a mutex called p underscore mutex, you'd want to use the address alpha operator, that ampersand, right? And p mutex, and that's your parameter right there. Okay, a couple questions for you guys to brush up on this. So question one, this is dealing with our mutex lock. Which of the following lines of code should be at line 16? And let's see, how much time should we give him, Chris? What do you think?
Just like 10, 15 seconds.
All right, that sounds good. Shouldn't be too hard for you guys. You can just type in the answer into the chat just so we don't have people talking over each other.
Yep, and D is the correct answer.
Yes. If you could just click one more time, Chris, so it should highlight D, right?
No, it moved on to line.
Oh, it moved on to the second question.
Yeah, I think so. That's a
Oh,
typo,
okay.
I think.
Okay, that's fine. Oh yes, why?
So, I did choose D, but I just wanted to ask. So, when it says like, I'm guessing that's the ampersand symbol, and then that's mutex in parentheses, right? I just wanted to ask.
Okay.
So what is that like? Is that referring to like the actual mutex or like the memory address to the mutex or?
You're talking about the parameter, right? Ampersand
Yeah,
mutex.
like what's inside the parameter. I kind of
Yeah,
forgot.
so remember from that last slide that showed the mutex lock and unlock, the parameter is going to be a mutex pointer, right? When you declare the mutex, you're declaring it as a pthread mutex t, but the parameter needs to be a pthread mutex t pointer. Pointers, as we all know, contain memory addresses, so if you have a regular pthread mutex t, you just need to convert that to a memory address, and we do that with the ampersand, which is called the address of operator.
Okay, thank you. That makes more sense.
Okay. All right.
Up to question
Anyone?
2.
Oh, yep. Okay, so which of these lines of code should be at line 20? All right, yeah, yep, you guys are correct. It's going to be A. There we go. All right. Anyone have any questions on why it's A? No? Okay. All right. And so this is just an example of one of the many examples we had in our lecture, which was like the bank system where you had like a withdraw and a deposit. So we have our withdraw with the mutex lock and mutex unlock uh, already implemented, right? And then just unlike the deposit function from the questions we just had, it's just showing you how it just removes the balance instead of adding to it. All right, so keeping in mind what you just saw, so which of the following lines of code should be at line 51? Keep in mind that you're passing to the deposit function, not the withdrawal function. This one will give you a bit more time. Try and remember exactly what parameters goes inside of that p3 create. Okay, give you all about 10 more seconds. See if they tell you. All right. So our correct answer is going to be C. Anyone got any questions on why it's C? Yes, the why.
So I am kind of confused on why C is the correct answer. Uh, I originally my thought process was to go for A, but to be honest, I wasn't. Uh, I was not really too sure. I
Mm-hmm.
just didn't know why you would do the void asterisk, but I can kind of see why you would have like null and deposit
Okay.
and that sort of thing. So maybe some, I guess, just some clarification.
Yeah, sure. So what do you guys remember? What is the last parameter for p3 create? As Chris is so helpfully shown on the screen. So as you can see, that last parameter, right, is the parameter that you need to, if the function you're using in the p3 create, if that needs a parameter, you need to be passing in something for that last parameter, right? Exactly, the parameter passed to the function. Like we said, you had to keep in mind what the deposit function looked like. Chris, if you go back to the deposit function slide really quickly. Yeah, here it is. Take a look at our parameter. What type parameter do we need? Yeah.
Are you referring to the? Are you referring to like the void asterisk arg?
Yep. And just like Christian said, yep, it's the void star. So since it's a void star, if we go back to our little answer choices real quick, Christian, or Christopher, sorry. So since we need a void star, right? We can't just be using this is question 4. Yeah, okay. So since it's the void star, right? We can't just pass in the memory address of PA. We had to convert it to a void star instead. Does that make sense to you all?
Why do we have the PA at the end?
So the PA is just the value that we're passing in. So in this case, let's see what's it called. What was it used for again? I think this is just the amount being right. No.
Yeah,
Yes.
PA is just the pointer
It's
for
just the
D.
pointer. Yep.
Is that because of what's on line? What's on line 50, maybe possibly, or like line
Yes.
44?
Well, it's no line 44 is just declaring PA as an integer pointer. You give PA a value at line 50, right? You set it equal to the memory address of the deposit. And that's why we use void star PA there. Right?
You
Because
could
if
also just directly use at D.
yes, you could do D. You could also use just D instead of PA, but you need to put the ampersand as well. So it'd be void star ampersand D. So yeah, Kwong, yes, you're right. Any other questions on this? It's a little tricky. Totally understand. So
So I kind of get why you put PA in the void star, but why would you in the like the way you guys wrote it for C? Are they like together as like one thing, like the
so
void star?
remember how we cast things, right? You have the data type in parentheses next to the variable. That's all it's doing. It's just casting PA to the type void star.
Okay. So it's just the data type next to the variable itself. Is what you're saying.
Yep. So you guys should have done it in your previous Java classes where you've say converted an integer to a double, right? You've just put the new data type, like in parentheses or something, next to the variable you're trying to convert it to. I don't know if that sparks some memories or not. It might have been a while ago for you guys, so
No,
but
that makes a little more sense because I do remember doing something
okay.
like that.
Yeah, because
It
that's
kind of rings a bell.
gotcha. That's all you're doing in that. You're just casting. Good questions. Any other questions on this one? Or shall we move on? Okay. Question 4. So which of the lines of code should we be using at line 55? And remember, we're passing to a void star function. Both deposit and withdraw use a void star function. I'll give you about the same amount of time as the previous question. Give y'all about 15 more seconds. Get some more answers in there. All right, and we'll cap it there. So for everyone who answered, yes, you are correct. It's going to be D. Um, any of you got any questions on why? It's pretty similar to the previous questions, so I don't assume there should be any, but just in case. Questions?
So you use ID2, which is another P thread, because you're using the withdraw function.
Exactly. So the only changes was that it's using ID2, and then instead of deposit, we use withdraw. Yes, why?
It makes a little more sense with this question. I can kind of see like the overlap, but I just wanted to ask, uh, how did you know that you would have to do withdraw, uh, based off like the lines of code? And then I think the ID too. I can kind of see that because we would have had to use ID1 for deposit, but I just want to know why you'd be able to look at that and know that you have to use withdraw.
Yeah, so it's a little context clues here. So we have int D and int W. So D corresponds to deposit and W corresponds to withdraw. Line 55 comes after the pthread create for deposit, right? So we would assume that you realize, okay, we've already have one for deposit. Now we should be using one for withdraw. So we get both functions. That makes sense to you?
So you're saying because we used it for deposit, uh, by like order, we would have to do it for withdraw if I'm like rewording you correctly.
Right, and also lines 53, right? You're using W, which corresponds to withdraw, right? So, and you're setting PA equal to the memory address of W. So we're overriding its initial value, which was the memory address of D, D for deposit. We're overriding with the memory address of W, W for withdraw. So now we need you to make one for withdraw instead of deposit. You see where I'm?
Yeah, that makes more sense.
Okay,
Thank you for the clarification.
cool. Any more questions? Can you please explain why do we need null in pthread create? Okay, so let's see. Chris, do you mind pulling up the different parameters for the pthread create? That slide again. Nice. Okay, so in pretty much every pthread create you're writing in this class, you are never really going to use that second parameter. It's for thread attribute objects. So since we don't really use that, we just use null since that's the default. So don't really need to worry about that second attribute. Is that good? Or yeah. So again, just don't worry about it too much. Just remember that second one's pretty much always going to be null, at least in this class. All right. Any more questions on question 4, or shall we move on? Okay. Question 5. So, which of the following lines of code should be at lines 57 and 58? So, just to give you a hint, this little section right here, we're wanting to wait for both threads to terminate, right? That's what we're looking for in this question. Which lines of code will wait for both threads to terminate? Give you guys about 15 more seconds. Should be enough time. All right, let's stop it there. Walter, come on, you got to choose one. Can't just do A or C. Okay, so the correct answer is going to be A. And the reason for this is because our parameters in pthread join, we're not looking for the memory address. We just want the pthreads. So you're just going to be using ID1, ID2, not the memory address of ID1, ID2. Any questions on this one? You guys are close. Just make sure that parameter type's correct. Lloyd, did you have a question?
So you were saying the correct answer was A because we should not have to reference the memory address for this question, is what you're saying.
Correct. Pthread join, it's the parameter that we're focusing on, not the return value, which is pretty much always going to be null in this class, but the thread, it's just the thread, pthread underscore t. It's not a pthread underscore t pointer, just a regular pthread underscore t.
So when we're doing like pthread join, what's the goal of that? Like what do you mean when we say like pthread
So
join?
pthread join, it's simply waiting for the thread passed in. You're waiting for it to finish terminating, right? So if we didn't have that, we might accidentally just end the program before the threads have finished terminating. Pthread joins just make sure the thread has finished doing everything it's meant to do, and then you can end off the program. Any other questions?
And just
Oh.
one last thing, sorry.
Yeah, go ahead.
What were you saying? Why did you say we did not need the like memory address compared to like the previous questions?
It's just syntax. That's really it. Pthread create needs the memory address, but pthread join just doesn't.
Okay, so that just has to do with syntax. So pthread create would require the memory address, but pthread join would not require
Yep.
the memory address. Okay.
And you can look it up in the Linux manual that you guys have used before. If you just look up pthread create and pthread join, they'll have the different parameters that you need to use, and you'll see that pthread create needs the memory address and pthread join just doesn't. So yeah. Any other questions on question 5? Okay, let's move on. Question 6. So, which of the following lines of code should be at line 22? And just giving you a little hint, this is essentially the producer consumer thing. So if you can remember what you did in there, this should be a little bit easier for you. And if you're having a little trouble, take a look at the critical version. See what it's doing. Give y'all about 15 more seconds. Any other answers from you guys before I reveal the correct answer? All right. We'll stop it here then. So our correct answer is going to be C. Count is equal to n. I see most of you answered C, couple A's. Anyone have any questions on why it's going to be count is equal to n?
What's the difference between 0 and n?
So n is, if you look at the very top at line 6, n has a value of 10, and at line 12 you can see that we're using n to define the size of our buffer.
Cool.
Yes.
Why?
So you're saying that it's count equals n
Mm-hmm.
because we have to use the buffer in the if statement.
Not because of that. So, like I said, when you had to take a look at your critical region, right? So, line 26, you have buffer at the current position incremented is equal to a random number. So, with this critical region, you're adding stuff to the buffer, right? And because you're adding stuff to the buffer, if you remember where this is going from the producer consumer example and the take orders process orders example, this if statement is going to be for that pthread condition wait and signal stuff we're going to add later. So we're just checking. So for this one, it's going to be the next line, right? It should be a wait if you remember from the example programs. So we're going to be checking, right? Since we're adding stuff to the buffer, we had to check if the count of stuff you're adding is equal to the size of the buffer. Because if, like Huang said, if the buffer's full, right? If a count was equal to n, you couldn't add anything anymore to the buffer without overriding stuff.
You were saying if count equals n, then we could not add more to the buffer.
Right, because
To
if you
override.
remember from the producer consumer example and your take orders process orders, this would be like your take orders function. You need to check if your buffer is full, because if the buffer is full, the next thing inside the if statement, right, was to wait for something, right?
So you would not have. So it would not be a because uh, because a has nothing to do with count equaling 0 has nothing to do with the buffer, and it doesn't have
Well,
anything to
it,
do
it
with.
does have something to do with the buffer. Count is just keeping track of how many items are in the buffer, right? So if count is equal to 0, that means the buffer is empty. But since this specific function, the producer function, is adding things to the buffer, remember that if statement is supposed to be the condition for the wait, the pthread cond wait. That means we need to be checking for a condition where we would want this function to wait. And we want it to wait when it's empty, right? Because we don't want to overwrite things in the buffer. That's why we use n and not 0. Because 0 means it's empty, which means the function could just keep writing new stuff and overwrite the old stuff.
Oh, okay. So then 0 uh, would represent if the buffer is empty.
Yep.
But in this case, it wouldn't be accurate to use 0 for the if statement on line 22 because it would be misrepresenting what the buffer amount would be. If I'm making sense.
Not necessarily misrepresenting, it's more of if we didn't have a check to see when it's full, we could end up overriding things that are already in the buffer with new inputs, right? So that if statement is checking to see if it's full, so we can stop the program or process for just a little bit, right? Because if this is a producer, that means there's another function here called consumer that will empty the array. So we need producer to stop when the buffer's full, so consumer can empty it out. And then, and only then, can producer go back to doing his stuff.
Oh, okay. Thank you for clarification.
Yeah, no problem. Good question. So any other questions on this one? On why we're checking for n and not 0 or any other thing? All right. Let's move on to question 7. So now that we're inside the if statement, which of the following lines of code should be at line 23? Give you all about 15 more seconds. All right. Guess we'll stop right there. So, our correct answer is going to be B. We get a yep. So, I think a majority of you got B. I think that's these couple that weren't. Anyone got any questions on why we're using B for our p-thread convoys?
So not full means that it has space to add to the count.
Yep, because it's not full, right? If it was not empty, that means there's stuff in it. Not full means it's empty. It's a bit confusing. That's why I suggest with the take orders and process orders that you don't use not empty, not full, because it does get a little confusing. But yeah. Any other questions on why we're using B?
What does so I know he went over what not full meant, but
Mm-hmm.
what does not empty refer to?
So not empty would be used for our consumer function. That would be probably below this, right? Because you have the producer and it's waiting for a not full so it could continue adding stuff, right? But the not empty would be for the producer, right? Because not empty means there's stuff in there, right? That means the producer can do its stuff and take stuff out of the buffer. Good question. Any other questions?
I think he did go over this, but I just wanted to ask, why did we need both of those parameters for the pthread conway?
It's really just syntax, really. You need, well, you obviously need the not full, not empty, right? Because that's the signal it's going to respond to, right? If the when consumer sends a not full signal, that means producer can wake up again and do its stuff. The mutex is most likely just to keep the keep track of which mutex it's using. Um, Again, you don't really need to worry about why it's there for this. It's more of syntax. Well, you do need to worry about why not full is there, but you don't really need to worry about why mutex is being used. Any other questions? Okay. Question 8. So, which of the following lines of code should be at line 34? I'm trying to think. Are we trying to signal producer to wake up, or we're going to signal the next function, which I assume is consumer, to wake up. Give you all about 10 more seconds or so. Any last minute responses? Okay. So our correct answer is going to be C. Does anyone have any questions on why it's going to be C and not perhaps B or D? Nothing? Yes. Why?
So, uh, when we say like the p thread can signal at non-empty, why, or maybe not why, the better way I'd want to phrase it is, how does this like order of like signaling work? The reason I chose C was because I kind of thought maybe it was like kind of like in reverse, like we would want to signal uh, the other mutex, but I'm not like really 100% sure on like the thought process. If you know what I'm like getting at.
Yeah, so the signal, right, is to wake up the other function. You don't want to wake up, you don't want to put not full because you don't want to wake up producer from itself because you're going to get stuck in this weird infinite loop where it goes to sleep because there's nothing in the buffer or there's too much stuff in the buffer and then it wakes up, but then again it checks and there's too much stuff in the buffer. That's essentially what would happen if you had the signal be not full. Because if you look at your conditional weight, right, you have not full in there, so it's going to respond to that signal. That's why you want the not empty, so it goes to the other process, right? So producer, if the buffer's not empty, it can do its stuff and add stuff to the buffer. Once it adds stuff to the buffer, it sends a signal to consumer saying, hey, put some stuff in the buffer. You can do your thing now. And then consumer, it will wake up if it's asleep because of that signal and then do its stuff, right? Is it at least one order in the buffer? So that would be that's one. If there is one order, then yes, that would be happen like that. If there wasn't, if the buffer was empty, um, it would just skip the if statement, right? Because count would be 0, and that's not equal to n. So it would just do its stuff, add stuff to the buffer, and then send a signal to um, consumer. Now, if the buffer was full, then the condition wait would trigger, right? Where producer would just stop doing his thing, and it would wait for a signal from consumer to wake it up when there's space in the buffer.
So it simply has to do with us trying to figure out what and when to use like not empty versus like not full. If that makes sense.
Yeah, exactly. Because your condition wait is going to have the signal, condition, sorry, that you want the function to wake up to. So in this case, producer, you want it to wake back up when there is space in the buffer, so you can add more stuff to it, right? But for consumer, you want that to wake up when there is when the array is essentially full or there's stuff in the array, so it can take stuff out of the array. So you need to identify which condition belongs with which function, right? And once you identify that, you can use it in the condition wait, and then you can use the opposite, the other condition in your signal to wake up the other function. Good questions. Anyone else have any questions on why we're using not empty? Okay. So this is just going to be your other function, the consumer. So like I said, with producer, you're adding stuff to the array, but in a consumer, you're taking stuff out of the array. And let's see what else. And then you have your main method in the other screenshot where you can see that the threads are being created, one for producer, one for consumer, so and so. Okay. So decomposition types. So remember, there's three different types of decomposition. We got data, task, and data flow. In data decomposition, you got different threads or processes executing the same function on different data. In task decomposition, you have the different threads executing different functions. And then the last thing, data flow, is one thread execute a function and produces data, and then the other thread takes the executes a different function and consumes the data that was produced. So that data flow, that's what we're using in the producer consumer. Producer produces, and then consumer consumes. Any last questions on data sharing before we move on to CPU scheduling? Yes, Loy.
So for data sharing, you were saying that we had strict alternation, but I remember you saying that mutexes were like the best way of going about it so that you didn't have interleaving. If I'm like getting that right.
Not interleaving, busy waiting. Remember the term, right?
Busy
You don't
waiting.
want busy waiting. And then there was one last method. Do you remember what it was called? Starts with a P.
Peterson's
Yes.
solution.
So, yep, those three. Strict alternation, Peterson's, and mutexes.
When you said did interleaving stand for anything, or did I just like remember that the wrong way?
You might have just remembered that the wrong way. The thing that we're concerned about with those specific three is the busy waiting, and that busy waiting is just when a thread is preventing another thread from taking its turn, right?
Is that the same thing when you say busy waiting? Is that the same thing as one thread interrupting like another thread, like how the professor was going over in the notes with the bank account
Yeah.
program?
So not necessarily interrupting, but preventing the other thread from taking its turn, right? That's the thing with like strict alternation. Even if, say, it's thread zero's turn, even if thread zero is not interested in taking his turn, thread one still has to wait for thread zero to take a turn before it can uh do its stuff. And that waiting, that's what we call busy waiting.
Okay, thank you.
Yep, no problem. Any other questions on data sharing? There'll be time for questions at the end too, but while it's still fresh, any other questions? right. CPU scheduling. Keyone, are you okay with going over this, or do you want me or Chris to do it?
I can go, yeah.
Okay.
So, let's see. Sorry, I didn't create this PowerPoint, so
Keyone, are you able to see the slides at like the very top in the messages? There's a link to the.
no, I don't see it, but it's
Okay.
okay.
All right. I think you can just go to the next slide, Chris, because the actual content's on the next one.
Okay. So these are the CPU scheduling policies that we went over. The first one is first come, first served. And like the name implies, the first job that arrives is the first job to run. And this is a non preemptive policy. So none of the jobs, once they start, will be preempted or interrupted. And then the second one is shortest remaining time first. And this works with the priority queue. So for this one, the job with the lowest remaining time in the current CPU burst is run. And when we say current CPU burst, if you remember in your assignments, some jobs had a CPU burst and then a input output waiting time and then another CPU burst. So when we say current one, we're just talking about one of those CPU bursts, not all of the CPU bursts combined for one job. And this one is preemptive. So a different job, if it has a shorter remaining time, it can interrupt the currently running process. And then the third policy is round robin, and this uses an enhanced queue. And each process is given the same set amount of time to run, and this is called the quantum. So if a process goes through a quantum without finishing, it gets put to the back of the queue. And the note says input output wait time takes the process out of the queue until it's over, and then once it is over, it'll be put back into the queue. So we'll go over some examples. And for more examples, please refer to the CPU scheduling test problems that your professor has provided you. It's available as a separate module in Canvas. And yeah, I would highly recommend going over these examples before the test because they will be the most similar to what you will actually see on the test and will definitely help you understand the algorithms better. So this example is the round robin example, and we have a quantum of 2. So each process will get to run for 2 times each. Each process is given 2 quantum. And the chart we have at the top, when we write down the letters, so we have DBCA, that represents the arrival time of each process. Okay. And what we have written below it, that represents the job queue. So D5 means D has remaining CPU burst time of 5. Okay, so because our quantum is 2, D ran for a time of 2, and then it gets put back to the end of the queue. And now B is the next available process in the queue, so B will run for 2 times. And once B finished, we can see let's see. D and C both have a time of 3. And because this is a tie, the tiebreaker that is used is to place the process that just finished its quantum before a newly arriving process. And so from this, we can see that the process that will go next is D. And now we see that Luai, did you have a question?
Yeah, I just wanted to ask about when it comes to the queues. So like how in the first, the arrival time was 0. You put in the 2 squares for D. So then right after that, for like number 3, B is up first. So then would you put D like right at the bottom, and then you would keep doing that as the round robin keeps going?
Yeah, so since D finished at time 2, it gets put back in the queue at that time. So in the picture, you can see at time 2 that D is written again. So that's what that means. D is put back in the queue at that time, and it has 3 bursts remaining. Did that answer your question?
Yeah, that made more sense. I just wanted to ask for a follow up for, so when you have when you have like D and then the reverse time, left is 3, and then you have like C on the bottom. So why did you put D as the first in queue for that one? If you know what I'm like trying to say.
Why is D at the beginning of the queue at time 4?
Yeah, that's the words I was trying to use.
Okay. So after B finishes, so after D went, and then D was put back in the queue, B went, and so now B, C, D, and A are all in the queue, but so sorry, trying to word this. Since B just finished, B gets put at the end of the queue, which means, and since D was in the queue after B at time 2, D is now first. And C arrived in the queue while B was still running at time 3, so C's next. And now since B just finished and A also arrived at the same time, remember for our tiebreaker, whatever job just finished will be put in front of the newly arriving time, even if it's at the same time. So B gets put next and then A. Did that help clarify?
Yeah, I'm just gonna try to like just reword what you said briefly. So
Mhm.
because D at the end of uh time 4, because earlier you had like B with the CPU burst time of 4, and then you had D. So then next at like time 4, D is gonna be the first in queue, if that makes sense, because it was like on queue before.
Mhm.
Is that like why?
Yeah, so D was already next in line after B. So after B runs, then D automatically is next in line.
Okay, thank you.
Mhm. So now at time 6, after D goes, C is next in line, as you can see. And so C only had burst time of 1, and this is shorter than our quantum. But in this situation, the next job will start right where C finished. So we don't waste an extra time. We just start with the next one, which in our case is B. So B will run twice. And now, since B already ran for 4 times, it now has a wait time of 2. And so we showed that with the gray lines and showed that the new arrival time for B will be at time 11. So it doesn't get put automatically at the end of the queue, it will be removed until time 11. And so then our next job to be put at time position 9 is A. And once A runs at time 9, A also has a wait time, excuse me, of 4. And so we have grayed that out and put A at time 15. And so now in our queue, what is left at time 11 is D and B. And so D did its remaining time, and then B ran for 2 times. And at time 14, B is the only one still in the queue since A has not returned from its wait time. And so at time 14, B will continue even though it just ran its quantum since it was the only available one in the queue. And B finished. So at time 15, A will run twice. And then A is still the only remaining job in the queue now, so it will finish the rest of its burst time. So does anyone have any questions on how we did this?
Do the practice sets like give you practice on all of this? Because this is just like a little something to follow.
Yeah, so the practice ones, I think we have 3, and each one has first come, first served, shortest remaining time, and round robin.
Okay.
Mm-hmm. Luai?
For round robin, round robin scheduling, uh, the IO wait times that's not involved here, right?
What do you mean?
So I mean, the way that we wrote the spreadsheet,
Uh-huh.
uh, the IO wait times, like for example, where it says 4 and 2,
Mm-hmm.
that didn't factor in to when we drew the illustration, right?
Yeah, we did factor in the wait time. So if you look at the picture, the grayed out parts, that's where we are considering the wait times. So for example, for A, at time 9 and 10, we ran for its quantum of 2, and that happened to correspond with its CPU burst time of 2. So after that, A gets its wait time of 4, and so we grade that out. And for that time, A was not in the queue. But after the grade out part at time 15, A gets put back in the queue, which is why we wrote A4 since it has a burst time of 4. And the same thing for B.
I thought that A, according to the chart, that the burst time for A was only 2. Or I wanted to ask like why you said it was 4. Maybe I'm just not seeing something.
Yeah, so the first burst time was 2, which is why the first 2, which is why we colored in 2 for its first quantum, and because the quantum and the burst time corresponded. And after that, we graded out for 4, which is the wait time of 4. And then after the wait time, there's another CPU burst time of 4 for A. Is that the part you're confused about?
Yeah. So is that because after the IO wait time of 4,
Mm-hmm.
there's that 4 that's like it's in the column, but it's not attached to like any particular job, but you would just automatically put it with A. Am I making sense?
Oh, in the table, so the CPU burst time of 2, wait time 4, burst time 4, that's all for job A. And then under that, CPU burst time of 4, wait time of 2, burst time of 3, that's all for job B.
Okay. So for A, you have 2, and the wait time is 4. But then that other 4 that's right before B's CPU burst time, that goes with A.
Right,
And the same type of thinking follows. B has its burst time and then the wait time. And then 3 is going to go for B's burst time.
right.
But it's not going to execute at like the same time exactly because of the quantum and having to like keep track of the queues and stuff.
Mm-hmm. Yes.
That makes more sense.
And I'll add that A only had a burst time of 4 because it was the only one left. And then
At the end,
B
yes.
had a burst time of 3 because it was the only one available.
Are there any other questions? Okay. I think we can move on. Or was this the last one? All
Yep,
right.
that's the last one.
Cool. All right. Any last questions, whether it be on CPU scheduling, data sharing, pthreads?
So will
Nothing?
this second test be like similar in like length as the first test?
I think it should be. Should be. Because you'll be doing it in person. So it's definitely shorter than last semester's. Because last semester was a little longer because we were
Okay.
all online. But yeah, it should be roughly similar to test one.
Interesting. Okay. Okay. Do we have access to test one to look over like what we got
So to
now?
look over your answers, you had to ask one of us, whether it be Professor Rama Prasad or whichever professor in. And for Professor Rama Prasad, you can also ask her TA. So me, he, Juan, and Rajesh. Not sure about the policy for um, our other two professors, Mayhouse and
God.
MacLeod. But at least for Rama Prasad, you can either ask her or one of us TAs.
Okay. Can I ask one of y'all now? Do I have to meet with y'all or something?
You had to
Or?
meet with y'all, or you had to meet with us. So if one of our if our office hours are like if they have the waiting room where it's only one person at a time, we could probably get you in there. Otherwise, you'll definitely just have to make an appointment with us.
Okay.
Cool. Any other questions?
For the round robin scheduling, what do you do when you have two what do you call it? What do you do when you have like two, like let's say you had A and B,
Mm-hmm.
they were gonna arrive around the same time, or like you had the scenario where their burst times were the same. How do you deal with like the queues and what goes first? That makes sense.
Um. Uh, could you repeat that again? Like, is there a specific one from like our example that you're talking about, or?
Oh no, it wasn't really. It was like more of a hypothetical thing. I think it was gone over in one of the rules, but I couldn't remember the question.
Yeah. So, are you asking about when one job like finishes at the same time that one arrives? Is that what you're asking about?
Yeah, that was part of it, and then the other part was, what do you do uh, when they're like the same length or like the burst time is the same? Is that
So, for the first part where one job's finishing and another job's arriving, it's going to be the job that's finishing. It goes into the queue first before the one arriving. As for your second one, it doesn't really matter how long of a CPU burst time these jobs have. It's whatever's in the queue, right? We're following the order of the queue. So if we're saying like A had a CPU burst time of 4 and B had a CPU burst time of 4, whichever one's in the queue first, that's gonna execute first, then the next one.
okay? I guess my question was more, maybe that wouldn't have to go with round robin, but that would have to go with like the first remaining or the
Shortest remaining.
shortest remaining. Yeah, I think that would matter more because with
Yeah,
that one, it's about choosing the one with the shorter first time.
exactly. For that one, yeah, you're gonna just check which one has the shorter time left, and then uh, do that. And then if they both have the same amount of time left, it's whoever came first that'll execute. Will test 2 have material from topics in test 1? No. None of our tests are going to be cumulative. They're all on certain set of modules. You're not going to have crossover. Yep, no problem. Any other questions, y'all?
Would you say, as far as review, that it would be a good idea if we went over the any of like the assignments with programming we did, if there was something that like didn't make sense?
Yes, because Um, just like test 1, you'll probably have some sort of matching and figure out where code, like which line code will go on. So make sure you brush up on, where your p-thread condition wait should go, and where should your mutex lock and unlock go, and which mutex should be locking and unlocking. So yeah, you definitely want to at least just go back and just quickly look through what you did in the programming assignments.
Okay, thank you so much for all like the clarification stuff. It was really helpful.
Yeah, no problem. All right. Anyone else? Daniel, Isaiah, any more questions from you guys?
Oh yeah, will we be able to go back and like see this or?
Yes, the recording. So Chris will send us a recording, and we'll make sure the professors post it as soon as we can get it.
Yep,
There
I'll send
should
the
be.
professors the slides and the recording.
Yep. There should be a module for you guys, the test 2 review session and slides. Just click on there, and it should be available in there. And she probably will post it on Campus Wire like she did for test 1 as